Have you ever wanted a waffle so bad you bought a literal ton of obsolete machine tool to make it happen? Last December, I found myself craving a waffle. Except there isn't a waffle iron up at the shop. So I started to think about how I could make one. Cutting concentric grooves into the end of a round on the lathe perhaps, and hinging two slices together to form something like an old pre-electricity waffle iron, the kind you would hold directly over a stove. But then those concentric rings got me thinking about classical labyrinths, and that's a form I've been meaning to work with for a long time now. I actually have a fairly complete design for a roller chain labyrinth, which I've been working on ever since my brother mentioned he wouldn't mind having a kinetic sculpture of mine. Well, I still haven't started on it, Chris, and I'm afraid maybe later this year? But yeah, why not make the waffle into a labyrinth? With a big reservoir into which you can pour the syrup, and then watch it slowly make its way out to the exit from there. A meditative, symbolic pilgrimage to start the day. Some thoughts can't be unthought. I was immediately committed to this idea. And it was something I could make on the rotary table on the mill. I'd need a list of radial coordinates. Then it would be a matter of rotating and translating, until the cutter had moved through the entire path. Except, it was going to take a lot of passes to cut something as deep as a tapered waffle groove. And doing it manually, the chances of finishing one without making a major mistake seemed close to zero. And I'd have to make two. It's one of those scenarios where CNC would really make a lot of sense, except I don't have any CNC machining equipment. My hobby is manual machining, and hobbies are a bad place to start mindlessly optimizing for productivity. It's okay to have a corner of your life not dedicated to capitalism, I promise. But yeah, it really would be convenient here. Of course, people machined complex shapes long before CNC. One of the ways they did this was with pantographs, a mechanical linkage of parallelograms that you might have played with as a child for copying drawings.
You can draw quickly and easily with the amazing Sketchograph. Pin down the Sketchograph firmly, guide the pointer over any map, picture or pattern. Using a felt tip pen, you'll get a faithful reproduction on paper, wood and most materials.
Depending on how the linkage is configured, this can scale it up in size, scale it down, or even skew it. Well, scale that mechanism up, replace the pen with a high-speed tool holder, make it a lot beefier with cast iron and precision bearings, and you've got a pantograph engraving mill. Until CNC really took off, these were commonly used to make injection molding dies and other complex 3D shapes. You can make a model of what you want out of an easily worked material like wood or wren shape, scaled up so it's even easier to make precisely. Then, with the use of pantograph magic, you could scale it down, cutting it into metal, which conveniently at the same time would scale down any errors you had made in the model. One of the reasons I like playing with old technology is to appreciate just how clever we used to have to be to get anything done before the universal solvent of cheap computation turned everything into software. Eugene Wigner didn't go far enough. Math isn't just unreasonably effective when it comes to natural sciences. Math is irresistibly useful in just about every field, at least in the form of software. But yeah, pantograph mills. They've mostly been scrapped over the last few decades and are pretty obscure now. But they're still super cool, and I've had one on my wish list for quite a while. If only I had one, it would be perfect for the Waffle Labyrinth project. I could explore an idea I've been thinking of as indirect CNC, where I 3D print a template that I designed in CAD, and then used a pantograph to copy that into a real material. But I didn't have one, so it was just another impossible idea bouncing around my head. And then not just one, but two more stars aligned for a truly great conjunction. A nice pantograph mill came up for sale locally for a very reasonable price, and my Christmas bonus came through. Well, what could I do but rent a U-Haul? The gods had spoken, and they wanted me to make a labyrinth waffle. It sat in the outer shop for a week or two as I carefully disassembled as much from it as possible. It was very heavy, but worse, this thing was top-heavy in particular. That makes sense as it's basically a vertical mill, which is already a top-heavy thing, with a complex linkage bolted on up top. But it did leave me a bit nervous about moving it around by myself. I also made a pair of 4x4 skids to bolt it onto, with rectangular nuts and milled slots, so they can be unbolted from the top if need be. These would help me with stability during the move, and also let me set it on the pallet jack, which I was otherwise unsure about due to the forks not fitting very well under the base. For the 84% of you new to the channel, since the last time I brought home a giant lump of cast iron, there's one important thing you have to understand. There is a 6-inch drop from the outer shop, where the garage door is, into the inner shop where the machine tools live. Combined with not particularly tall ceilings, this has at times made moving equipment really interesting in the pejorative sense. Particularly that time I almost let the bandsaw tip over, because the only way to make the geometry work was to move it through the doorway while leaning back at a 15-degree angle. It all ended up okay, but I wouldn't try it again. Thankfully, this time went a lot smoother. I tried something new, including the pallet jack in the stack of blocking, so that after sliding the mill in and removing the roller pipes, it could be immediately moved away from the doorway. This made removing the rest of the blocking a lot easier and thus safer. If I'm going to be crouched down operating a toe jack while a ton of cast iron tips back and forth above me, I really want to be out in the open so I can flee in any direction if things go pear-shaped. At first I placed it next to the shaper, but that made access to its electrical panel almost impossible. So I moved it over to the wall next to the rotary phase converter. This also made wiring it in a lot easier, as when installing the conduit for the 3-phase line over to the bandsaw a few years ago, I included a couple blank junction boxes for future outlets, should I ever get more 3-phase equipment. Good thinking past me. The inner shop is definitely starting to approach the status of cramped, but I still have room for at least one more major tool acquisition if I move the metal storage to the outer shop where it really belongs anyway. Maybe a surface grinder or a horizontal mill? Well, not anytime soon anyway. I spent a couple weeks just getting to know my new friend. It is a Frederick Deckel KF1 pantograph mill from sometime in the middle of the last century. It was a seriously nice machine, though this one hasn't had an entirely easy life. Basically, you put the thing you want copied on the right-hand table, the copy-holding table, and trace around it with the pantograph stylus. This moves the cutting head on the table on the left, the work table, in the same path in all 3 dimensions, or one scaled up or down depending on how you have it configured. First, I needed to be able to operate the collets on both the stylus and cutter side of the pantograph. Luckily, mine came with a good range of sizes for these, as they're ridiculously expensive, but it didn't come with any wrenches for actually operating them. These were the relatively specialized sizes of 42 and 42 millimeters on the cutter side, and 36 and 32 millimeters on the stylus side. Ideally, I wanted a pair of 42-36 and 42-32 millimeter double-ended wrenches so that just the pair of them could serve both jobs and they would just live by the mill. Failing to find any, I drafted up a simple wrench design which I sent off to get cut. Solved. The pantograph has lost its speed-adjusting CVT, unfortunately, an event that this rather clumsy repair on the cowling suggests was at least moderately energetic. It's been replaced with a simple fixed belt drive, which in turn drives the round belt which runs out to the cutting spindle. The round belt that came with the machine was shedding fiber every time I turned it on, so I figured it was best to replace it now. I got some urethane round belting, and finally got to try that trick I'd seen, where you heat up a thin piece of metal like a razor blade, push the belt against this from both sides to melt the ends, then slide them up off the blade into contact with each other, welding them into a single loop. And it worked, first try. Mine also lacks the attachments needed to either scale up or down in size while copying apart. Scaling up isn't much of a loss because you can't really cut hard metals that way anyway. The leverage is working against you and you can't maintain control of the cutting end. Or at least, that's my purely theoretical understanding. But being able to scale down really would be nice, if only just to be able to engrave text at a reasonable size. Spare parts for these are rare and pricey, but I think I should be able to make my own. But that's a future project. I bought a set of engraving letter templates to play with, and shortly after learned that the name for this weirdly ubiquitous typeface is Gorton. It's iconic yet anonymous, which is a really cool combination. The letters turned out to be a bit large, as the oddly shaped volume which the stylus can reach can only handle a couple letters at a time, but it did make me feel more confident about setting things up for copying. So it was time to get serious about the waffle thing. After failing to find one at local Goodwills, I ordered the cheapest waffle I could find that had removable plates, and set about designing my replacements. As well as mimicking the overall dimensions so it would actually fit in the waffle iron, I also made the slots on mine have the same profile. 20-degree sides, half an inch deep, and about 1/8 of an inch wide at the bottom. I wasn't able to find any academic literature on proper waffle draft angles, so I figured it was just best to copy. At first I directly designed the waffle, so I could work things out like how many concentric rings there would be and what the path layout would look like. The number of rings has to be odd, or else the path would have to cross over itself, so I went with 3, as 1 would be degenerate and 5 was right out. But what I needed was a design for the plate that would make the waffle, not the waffle itself. I needed to make a waffle negative, that is. And the plate had to be machinable, which meant the path had to be something a cylindrical or conical shape could move through. So you can have sharp exterior corners, since that's just a cutter moving in one direction, stopping, then moving in another. But all the interior corners have to have a radius, that of the smallest cutter you'll be using. With the general design worked out, I could print a template and start cutting. But there were two different ways I could see to do this. The template could be basically two-dimensional, just a recessed slot that the stylus would run in, following the center of the path that the cutter would need to take. After each pass, the work table would be raised a bit, while the template and the copy holder table stayed in the same place. To cut the tapered sides of the slots, I could first hog out most of the material with a series of cylindrical end mills, then finish it with a tapered end mill. This would mean the last pass was cutting a lot of material, but I was planning to do this in cast iron, which is quite machinable, so I was hoping that could work. The other option would be to print out a full 3D template of the entire plate. On the pantograph, between each pass, both the copy holding and the work holding table would be raised slightly. This means the stylus would trace out a slightly different path as it worked its way down the tapered sides of the slots. The majority of the material could still be removed with normal cylindrical end mills, but the finishing passes would be done with round nose end mills. This would require a lot more passes, but the amount of material being removed at each one would be kept quite small, so I was sure the cutters could take it. However, my selection of round nose end mills was pretty limited, so I went with the 2D idea to begin with. The print failed halfway through, but at least I could set it up in the pantograph and try the basic idea in steel. And it seemed like it would work, so I printed the template again, this time successfully. It was right at the very edge of my print volume, only fitting if I placed it vertically, running from one corner to the other of the print plate. I even had to go with 4 clamping lugs instead of 3, so that they could be placed 90 degrees apart and not add to the height. It worked this time, but unsurprisingly it was one of the longest prints I've ever done at almost 15 hours. I did another test with it, this time going to full depth in wood, partially as a way to procrastinate, and partially because I thought it would look cool. Have I mentioned I'm into the whole labyrinth thing? Not being able to put it off any longer, I ordered the metal and tapered cutter I would need to do it for real. I wanted to make it out of cast iron. First, because cast iron is traditional for waffle irons, that's what the iron refers to, but also because I really like working with it and don't get the chance very often. Now, it does make a huge mess. It's 2 to 3% carbon, and ever look inside a pencil sharpener? It's kind of like that, but the entire shop. But it's so machinable, you would have to actively work to get a bad surface finish with it. All that graphite makes it self-lubricating, and you can take surprisingly deep cuts and it just crumbles away. Plus, I just think machined cast iron is gorgeous. If you could get over the millennia of cultural snobbery, I really think that the luster of machined cast iron would be ranked as highly as that of gold. I needed 2 discs that were 3/4 of an inch thick and a bit over 7 inches wide. This meant I had to order 1-inch thick discs that were 8 inches wide. Except when they turned up, they were more like 1.3 inches thick. So could I have ordered 1/2 inch thick discs and they would have turned up thick enough to work with? We'll never know. First, I cleaned up the faces, which again was running things right at the edge of the envelope for my equipment. With that done, I drilled and tapped a blind hole on one side. This let the blank be threaded onto a mandrel held in the 3-jaw chuck, giving me complete access to the front, sides, and most of the back. You might think machining is about cutting metal, but that's actually a distant third after thinking about work holding and order of operations. Using this new mounting, I could turn them down to the final thickness of 3/4 inch, generating an endless stream of powdery chips in the process. I admit, I'm really including the shot to see how the YouTube video encoder handles something so close to pure noise. The front face wasn't made entirely flat though. I left a raised nub in the middle, in which I drilled a temporary 1/4 inch hole. This would provide easy centering when I set them up on the pantograph. It wouldn't matter how the blank and the template were rotated relative to each other, being circles, but they would have to be exactly the same distance apart as the pantograph stylus is from the cutter, or else the labyrinth wouldn't be centered properly in the disc. The easiest way I could think to do this was to include a centering hole in the middle of each one, mount rods of the same size in both sides of the pantograph, place these in the holes, and clamp everything down. Simple. As I had planned, I started by using a series of normal cylindrical end mills to remove the bulk of the material. This worked okay, though because of my limited speed control of the cutting tool, it definitely worked best at about 3/16 inch and was getting a bit rough at 3/8. Because I was cutting down into what would be a tapered slot, the depth each one could cut to was different depending on their diameter. I'd work out this target depth after changing the tool, then do a series of passes following the template, raising the work table between each pass until I had reached the target depth for that diameter. Pantograph machines like this are sometimes called die sinking because of this process. You sink the design into the die being made, with each pass being a bit deeper. Once this was done, I was left with a path cut all the way down to half-inch depth with stepped walls. All that was left was to cut the tapered size using this tapered end mill I had ordered for the purpose. I started with the work table raised, so it was just barely cutting, then followed the same process of raising the table between each cut. Unlike the cylindrical tools, however, this meant it was cutting more and more material with each pass. This was where my relative lack of control over the RPMs became a real problem. As it approached the bottom of the slot, it started to sound pretty unhappy. And worse, it didn't seem to be removing much more material when the table was raised. A closer look showed that, yeah, it had not survived the attempt unscathed. I had been thinking that cast iron was machinable enough that this wouldn't be a problem, but, well, my machining instincts are still a long way from perfect. It was time to pivot to the other approach. I printed the full 3D template, and it mostly came out fine, except for this kind of squishy, distorted section. This has been happening in the very center of the print volume for me recently, possibly because of an FEP that needs replacing, but it only affects the first few centimeters of the print. In this case, I thought it would be fine if I just filled it in with wood filler, a decision I would definitely not come to regret almost immediately. The setup on the pantograph was the same, and it started with the same process of bulk removal using the cylindrical end mills. Unlike before, when I had raised just the work table between each pass, this time I wanted to raise both tables. That way the stylus would work its way down the sides of the slots just as the end mill was doing the same. But that's a really awkward and error-prone process for something you're going to have to do a lot. It would be way too easy to let the tables get out of sync with each other, ruining the part. Luckily, the engineers at Frederick Deckel weren't fools. You can turn this single dial up top, and that will raise and lower the entire pantograph mechanism as a unit. There's even a little ratcheting device on the wheel, which lets you quickly and easily increment it by a set amount. This thing might seem like just a quirky oddity now, but a lot of thought went into making it a practical tool for industrial uses. One thing I didn't consider is that, before, it was the sides of the stylus rubbing in the slot. Lots of surface area between the two. But now that I was tracing a full 3D template, only the bottom edge of the stylus was in contact. And it can take a decent amount of force at times, because the other end of the pantograph is being pulled through metal that it is cutting. If you've ever felt the resistance on the hand wheels on a manual mill, you'll know it can be significant at times. So the stylus can end up being pushed into the sides of the template with quite a bit of force. And if that part of the stylus is a sharp edge, and the template is soft plastic, it can start to cut in. Mostly this wasn't catastrophic, but that wood filler? It got turned into powder, a bit more with every pass. The underlying print even cracked eventually, being so thin. I tried to keep the stylus away, but the cutting forces made that very hard to do reliably. I just ended up having to accept it as a learning experience. If I ever have to patch a template again, I'm using epoxy putty. But as soon as I switched to round nose end mills for finishing the slot, I also realized I'd been being silly about the styluses to begin with. At first, I was going to make a new stylus for each size of round nose end mill, but because all I was doing was cutting the sides of a taper with a constant angle, I realized I just needed a single tapered stylus, with a tip that was rounded to the same radius as the smallest end mill I was going to use, in this case 1/16 inch. As long as I set the relative height between the tables correctly to begin with, this would always keep the cutter at the right height. I wouldn't have to worry about doing the trig like before, because the bit of the stylus projecting below the area being cut would prevent it from getting too low. Once that hit the bottom of the slot, it would be time to switch to a smaller round nose end mill. And, more importantly here, the surface of the stylus in contact with the template would be more than a single sharp edge. If I had started with this, it's entirely possible that the wood filler never would have crumbled. Yet another learning to be experienced, I guess. After making the round nose passes, the slots were looking pretty great, though the faceting of the sides of the 3D print were quite obvious. I had forgotten to turn up the export quality parameters when generating the STL, and frankly I didn't think it would be particularly obvious in the final product. But yeah, it turns out you can copy some really fine detail with these things. There were plenty of more minor problems, usually from where the cutter had caught and pulled itself a bit too deeply into the face it was cutting. There is definitely a skill in avoiding that I need to develop. It really makes you conscious of the difference between conventional versus climb milling in a way that even using a normal mill doesn't. This is the difference between moving a cutter into material with its rotation or against it. Normally, you want to move it opposite the rotation. This means that as the teeth bite in, the cutting forces tend to deflect the cutter towards the material. It can't do that since solid material can't pass through other solid material very easily, so it doesn't deflect much. This means you can take deeper, faster cuts, though the surface finish isn't always so great. It's called conventional milling because that's how you make most cuts. Going the other way is called climb milling, because now the cutter wants to deflect away from the material, lifting itself up into open air. That's a lot more possible, and the cutter will happily snap itself in half if you try to take too deep of a cut when climb milling. But the surface finish tends to be nicer, so you will often do almost all your material removal conventionally, and then take one final light climb pass to clean things up and take it to final dimension. And not surprisingly, you can really feel these forces at work when the cutter is at the other end of a pantograph. There was also some roughness at the top of each slot. I had started with my last 1/4-inch end mill on those, and it was a bit dull. Combined with the less than perfect feeds and speeds, it had resulted in a fairly rough cut there. I tried to clean this up with a couple more passes on the 1/4-inch round nose, but this ended up widening the slot considerably with a fairly awkward transition to the lower sections. I now realize that what I should have done was use the tapered end mill with the full 3D template. Then it could have slid down the sides of the slots, removing just a small amount of material with each pass while perfectly maintaining the angle of the slope. I am experiencing learning all over the place here. I definitely wasn't happy with the second plate, but it was also definitely better than the first one. And this might sound a little bit funny, several months into a project to make a custom waffle, but I'm trying to get a bit less precious about my projects. I mean, it's great that I can finally make things that even look a little bit close to as good as they do in my mind to begin with. But just because I can doesn't mean I always should. Timelines have been getting way out of control, and I want to get better at only applying the highest levels of effort when it's really called for. Plus, those cast iron disc blinks weren't cheap, so I decided to continue with the 2 I had and see what the final product looked like. If nothing else, I could validate the other machining steps I had in mind before I ordered more metal. This meant first cleaning them up on the lathe, removing the temporary central boss now that it was no longer needed, and turning on the sides to the final diameter as that extra material is no longer needed for clamping to the bed of the pantograph. Then they went into the rotary table on the mill, aligned first in X and Y by sweeping the perimeter, and then clocked in rotation so that the exit slot was aligned with the Y-axis. This was all just so I could cut the slots where they mounted in the waffle iron. This didn't have to be done on the rotary table, but this let me cut those slots concentric with the overall disc, which might seem a bit precious, I'll admit, but also it let me cut these long grooves around the outside to match the original plates. Batter gutters, as I've been thinking of them. This couldn't be done on the lathe, or else they would have intersected with the mounting slots, see? So the rotary table was definitely justified. Now that they no longer had to be held from behind, they went back onto the lathe to have the last of the material removed from their backsides, so they would actually fit into the waffle iron. And they fit. Except they still needed a little tab so they would be held in place by this toggle mechanism on the iron. On the original plates, it could be screwed directly onto this little boss, but those were die-cast and could have random features like that wherever needed. Since mine had been turned on the lathe, that didn't work, so I had to make long sheet metal tabs that screwed into the bottom, where there was still enough material to drill and tap 2 small holes. This was one of those almost trivial final tasks that is way more of a hassle and takes way longer than you expect. But finally, the labyrinth waffle plates were complete. They just needed to be tested. I started with a smoke test without any waffle batter, just to see how the iron would handle them. They are considerably more massive than the original plates, which are die-cast from some light aluminum alloy, and have as much material removed as possible to keep costs down. Only the exact areas above the heating elements are full thickness. Otherwise, you can see all the way down to the back of the little divots at the bottom of each waffle cavity. Theoretically, I could have done something similar in the pantograph, but I don't mind them being heavy. I quite like it aesthetically, in fact. That is, as long as the waffle iron can get them up to temperature without melting down in the process. It took over 10 minutes to do so, with the plastic on the top face getting to an eye-watering 130 degrees Celsius in the process. You can actually see the thermal expansion at work in the time-lapse. But the only smoke released was from the freshly machined plates themselves, and I couldn't find any discoloration of the plastic once it was back down to room temp, so I figured there was no reason not to try it for real. But first, seasoning. We were cooking on metal a long time before modern non-stick coatings. One classic way of doing this is with seasoning, which is when you wipe oil on a surface and bake it in place. It polymerizes into, basically, a natural plastic that both protects the surface and serves as a kind of non-stick coating itself. This is what people get so weird about with cast iron pans, but there isn't much to it in practice. I spread a thin layer of vegetable oil around and baked them at 450 for an hour, and they were seasoned. Still not entirely trusting how hot the iron got, I did the cooking in the outer shop, where fire and smoke are moderately common occurrences. It got up to temp fine and I added the batter. I was aiming to cook for 5 minutes, but after about 3 I heard a click. Neither light was on and the temperature started dropping. I wish I had a thermal imaging camera so I could show you, but trust me, the iron was dead. When it had dropped low enough, I figured it was no longer cooking. I opened it up, and the poor unfinished waffle was brutally torn in half. Disaster. It was at this point, staring at this sad mess, that I realized I had forgotten a machining step. I had never lowered the interior sections of the plates, meaning the tops of the walls between waffle channels would be in contact with each other once the iron was closed. Not all the batter actually squeezed out, of course, but in effect what I had been cooking was a long, thin, labyrinth-shaped waffle tube, and that was going to have to be fixed. But so would the waffle iron. It still wouldn't turn on, even after cooling all the way down. I'd been hoping it was some kind of thermal breaker that would reset itself, but this thing was way too cheap for that. After taking it all apart, I finally found this blown thermal fuse. So I could either look for a replacement part or just buy a whole new waffle iron. Or I could enter the forbidden "do not try this at home" zone and just bypass the damn thing. So yeah, that's what I did, but I really do strongly recommend against doing this kind of thing. I knew I would be running it on a steel welding table in an unfinished shop space with good ventilation and a large fire extinguisher and a barrel of water and easy access to a garden hose. But this is the kind of thing that if you mess it up and there is a fire, insurance isn't going to cover anything, and there could be legal implications. If you tamper with the safety devices on an appliance, you're on your own, buddy. So, not just because I've never had a chance to say this before in a video, do not try this at home. Even if the appliance in question is smiling at you as you disassemble it. Before the second live test, I put the plates back on the lathe and faced off 2 millimeters from the middle of each one, to save room for the connecting bits of waffle. And then re-seasoned them, of course. I also pulled out my big shop fan to try and provide a bit more cooling to the outside of the iron. And this time, we made it to 5 full minutes without the iron melting down, and the exterior only got to about 90 degrees. I gingerly opened it and it tore in half again. But it was looking much better. The halves released from the plates without much effort, which was very relieving to see. I almost would have been happy with them, but I still had a full mixing bowl of batter, so I tried another round, this time waiting 6 minutes before opening it. And with a little bit of care, one entire labyrinth waffle emerged.
You guys, it works.
And after all that worrying about the steps in the side of the first plate, or the tessellated sides and the bulge in the second plate, none of that was particularly visible in the waffle itself. So yeah, I really do need to learn to be less precious about these things. But the final test still waited. What would the syrup pour be like? Would it flow out in a stately, sugary pilgrimage? Not really. Not with cold syrup anyway, on an unleveled, non-planar waffle. And it turns out most waffles are neither leveled nor particularly planar. But with a bit of patience and some careful tilting of the plate, it finally made it to the end. And you know what? It actually was kind of meditative.